You may have heard about Latent Space, the engine behind almost every modern AI. But what exactly is it? To understand that, we have to look past the image and see what the computer sees, not a face, eyes or ears, but a massive grid of numbers. While we often use images as the easiest way to visualize this concept, the principle applies to everything from text and music to complex physical signals. Our goal is to turn this chaotic mess of pixels into a map of meaning. Let's dive in. Assume we have a large dataset of animal images. Each image's size is defined by its height, width, and color channels. For instance, RGB images. For example, if our image's height and width is 128 pixels, the total number of values needed to represent a single image is the height times the width times 3, which results in nearly 50,000 values. This large number dictates the dimensionality of the space where these images live. In this coordinate system, we have 50,000 axes, where every axis represents the intensity of a specific pixel. Natural images, the ones that actually look like cats or dogs, occupy only a tiny fraction of this enormous space. This leads us to the manifold hypothesis. It suggests that high-dimensional data, like natural images, actually lies on a lower-dimensional curved surface, a manifold embedded within the high-dimensional pixel space. This manifold is like a thin, folded sheet of paper floating in a massive room. Because the manifold is so small relative to the total space, the chance of randomly sampling a point and hitting a recognizable image is practically zero. You would almost certainly get uninterpretable noise. Also, learning the underlying distribution of natural images, which would allow us to generate new images, is one of the hardest problems there is. So if we can't easily navigate this massive pixel space, how do we find that subspace of meaningful images? We can train a neural network, an encoder, to map the image directly to a compressed representation, such as a vector of only 128 values. But since we don't have labels for what these 128 values should be, we introduce a second network, the decoder. The decoder's job is to take that compressed vector and reconstruct the original pixels. By forcing the image through this bottleneck of lower dimensionality, we pressure the encoder to discard noise and extract only the most essential features. Recall that in the original pixel space, every axis was just a raw intensity level. But in this new compressed space, every axis represents a specific feature filling the entire space. This organized feature-driven environment is what we call the latent space. It is named latent space as it is hidden from us and we need to somehow unveil it. Since every axis in the latent space represents a specific feature, when taking an image and extracting the latent representation vector of this image, we are able to control it. For example, some feature can be related to the ground type, and by modifying it, we can alter it from a yellowish dry ground to rich green grass. If we now change another specific feature value, which may relate to the pose of the main object, we can rotate it easily without changing anything else in the image. This is the beauty of the latent space. If the features are extracted correctly, they can also be modified easily, changing the input image to our desire. The encoder-decoder process we showed is basically a mapping of the image from the pixel space to the latent space using the encoder, extracting the input image's latent vector. From there, we use the decoder to go back from the latent space to the pixel space, where we can visualize the image again. This entire network is most commonly known as an autoencoder. So after training the autoencoder to reconstruct animal images, we now have a latent space representation. What do we actually see there? To build some intuition, we can visualize this space in a simplified way. We observe that images of similar animals tend to cluster together in specific regions. Cat images might form one cluster in orange, elephant images in blue, and eagles in the red cluster. The model has learned to extract features that represent each type of animal. As a result, images that share similar feature combinations like those of elephants are mapped close to each other, and the same happens for other animal classes. If we zoom in, however, we notice large empty regions between these clusters. So what happens if we sample a point from this empty space? Will we generate a new image? Or if we pick a point midway between the cat and eagle clusters, will we get a meaningful combination of the two? Let's see. We take an image of a cat and pass it through the encoder. We can see where it lands in the latent space. If we then decode it using the decoder, we obtain a reconstruction of the original image. But now let's take that latent representation and slightly move it to a nearby location, still within the same cluster. If we decode it again, what do we get? The answer might surprise you. Instead of a clean new image, we typically get a blurry variation that mixes features in an unstructured way. Moreover, what happens if we sample from the latent space between clusters? Here, the situation is even worse. The output will most likely be a blurry, unrecognizable image. So we hope that by building this feature space, we could smoothly edit image features or generate new ones. Why doesn't it work as expected? The reason lies in how we define the task. The model is trained to minimize a reconstruction loss. We ask it to reproduce input images as accurately as possible, and it does exactly that. But we never explicitly told it how the latent space itself should behave. The fact that clusters emerge is just a byproduct of learning to reconstruct images. It does not guarantee that the latent space is structured or navigable. We can see that the empty regions between clusters contain no meaningful representations. Even within a cluster, points are simply grouped together without a smooth structure connecting them. To enable smooth navigation, we need the latent space to be continuous and well structured. With such a space, we could move through it and generate meaningful images. We can interpolating within a cluster or even creating new hybrid concepts. For example, a blend between a cow and an eagle, or even a kangaroo with a dog. But there is a catch. Not all features can be perfectly separated. For example, we might try to change a feature related to lighting, turning a daytime scene into nighttime. But if we look closely, we may notice unintended changes, like the shape of the elephant's trunk also shifting. This phenomenon is known as feature entanglement. Sometimes it is undesirable, as in the trunk example, but in other cases it reflects real-world dependencies. For instance, when switching to a night scene, we expect shadows to change or disappear as the lighting conditions change. So how do we create a smooth and structured latent space? This is at the heart of generative AI, and in future videos, we'll dive into the different approaches developed to address this challenge. Thank you for watching, and I hope to see you in future videos.